First, I would like to thank everyone really for attending. I know everyone has busy schedules, and I really appreciate that you could take some of your time and attend this tutorial. And our goal is, and that's the main goal here, is to hopefully that we can present something new, like some new concepts that you can take it from there. So I'm really happy to see everyone, and we can get started. I don't want you to wait more. Maybe people will start to come afterwards. So yeah. So my name is Abder-Rahman Ali. I am a research fellow at the Center for Ultrasound Research and Translation, which is at the Massachusetts General Hospital and Harvard Medical School. So today's tutorial will be about radiologist in the loop. So it might be a new concept. So it's like an old concept, but maybe the new thing is that it is more adapted now to the radiologists. So about the agenda for today's tutorial. So the first two parts will be some theory about the topic. So I will be explaining what the radiologist-in-the-loop AI means. And then we will talk about active learning, which is a special case of the data-centric AI. And after that, from uncertainty sampling and diversity sampling and labeling instructions, those will be mainly shown as a real-world example. So after theory, we will be showing you how you can take that into practice. And if you have any questions throughout while I'm talking, please feel free to interrupt either by typing in the chat, or you can interrupt me. That's totally fine. The most important thing today is merely to learn some new things. Yeah. So yeah, let's get started with the radiologist-in-the-loop AI. So I mean, let's start with a definition of the concept, and then we will be gradually moving in how you can apply that into your practice. So when we say radiologist-in-the-loop AI, so there are two parts here, as you can see. There is the radiologist and there's the AI. So this concept means that we will be working with some strategies or methods, and the aim of those methods is to bring the radiologist, which is the human factor here, with the AI system, which is the machine part. And the goal of those strategies, by combining the power of the human and the radiologist in particular, and the power of the machine, the goal of bringing that combination together is that the end goal is to make our radiological AI application more accurate. So here, from now, moving from here onward, we're assuming that we're building a radiological AI application, but you can apply the concepts in any domain. So don't worry about the domain, but just to be on the same page, we're assuming that we are working on a radiological AI application, and that's the example that I will be showing towards the coming slides. So again, the goal is to combine the human factor with the algorithm factor, which is our AI system here. And the goal here is to reach higher accuracy, which is what we all want eventually. Either we are working on a classification problem, like if you want to classify between two diseases, you want your model to be as much accurate as possible so you can deploy it to the real world. And that applies to any AI application we are working on. Now, here in this slide and the coming two slides, I will be explaining the general framework of the radiologist AI system. So say, for instance, you said that now you are working on an AI application and you want to adopt this concept, the radiologist-in-the-loop AI. There are three main stages to the framework, and that you would be working with to consider yourself that you are using this framework. So in the first step, you would consider that all your data is unlabeled. So let's say that you have now, as working on radiological AI, that you have some medical images. Now you have a data set of unlabeled data, completely unlabeled. Now, the first step here in this framework is that you would randomly sample. So here, nothing different from the traditional machine learning till now. So we're just picking some images for the radiologist to annotate. So that's people who are working with AI, that's very familiar. So at the first step here, you would pick some random images and you would give them to the radiologist, which is the domain expert, to label. Now, the new thing here that in this first iteration, whatever data you have labeled, you would consider them your test data set. So that's the first step of the framework. The second step of the framework, now on this part, you have labeled some data in the first step. So here you have now a combination of some unlabeled data and some labeled data. Again, here, as the common way, you would randomly pick some unlabeled data for the radiologist to label. But this time, this labeled data would be your training data set. Now, this is the new part here. This is the new part here. You will have, like, say that you have a convolutional neural network. Let's just make it simple. And you're building a classifier. Now, what your model will be doing now is that it will use this training data that you have so far to train. You will use it to train the model. But now in the prediction, you will be doing the prediction on your original data set. We're not doing any testing so far. We're just trying to pick the data that matters. And this is the main concept here, to add to our training data. Because now we started randomly, but in this tutorial, we will be learning how to systematically choose our data for labeling rather than randomly. So what your model will be doing is it will be predicting, giving some predictions to the unlabeled data. So that's the second stage. Now this step will be repeated. So as you can see here, now that's the new concept here. So now, rather than picking your unlabeled data randomly, let's just go one step here. From this prediction that you did, the prediction, each unlabeled image will have a prediction. So what you will be doing here is that you will be picking those unlabeled images that your algorithm was not confident enough. And that's what we will be learning. So don't worry about how this is done, because I will be showing a real world example of how to do that mathematically and using a program. But the concept here, and that's what I want to emphasize here, is that after your first iteration, where your model gave you some predictions, rather than randomly picking data every time for the radiologist to label and add to the training data, this time you will be picking only the images that your model told you that it's not very certain about. Like the model thinks that it's not sure whether it belongs to class A or class B if we're working with a classification problem. So to recap, the radiologist in the AI framework has 3 steps. The first step is that you have unlabeled data, and the first iteration of the framework is that you will randomly pick some data for the radiologist to label to add to your testing data. The second step, you will also randomly pick some unlabeled data to add to your training data, but from that step onwards, you will pick only the data that your model is telling you it has low confidence in predicting their labels, for instance. So here, the radiologist in the AI, the radiologist in the AI framework, as you can see, the radiologist, if we go to the definition again, 2 parties are involved. There's the radiologist, which is the human part, and the machine. So as you can see here, there's in each step we're working with, we always have the radiologist involved and the model, which is the AI involved in each step. So the model is telling me as a machine learning researcher or engineer what samples it is not confident in predicting, and I am taking that from there and asking the radiologist only to label those samples. So that's the core concept of the radiologist AI in the loop AI. Now, what you have seen so far of picking data systematically for the domain expert to label is called active learning in literature. So if you want to dig more deep in that concept of how to systematically pick data for labeling, you would be involved more on active learning here. So I will give a high-level introduction of active learning, and then I will handle it to my colleague, Pang Gu, who will talk more about the theory of active learning. And after that, we will be more practical. So sorry if it's a bit boring at the beginning, some theory, but we will then go to some real examples. So if we come to active learning, so let's give a definition for active learning. So active learning are the techniques that we use to sample data. As you saw in the previous slide, those techniques will help us to sample the data that matters for the radiologist to label or annotate. So that's active learning. So from now on, and that's the change in our mindset in this tutorial. So the goal here is to introduce a new mindset in how we develop machine learning algorithms, is to focus on the data and keep our algorithm constant. And that's what I will show you, how using a simple neural network like that, how a simple neural network with the correct data can achieve high performance. And that's the new mindset that we want to learn today. So now we will no longer just pick data and label that data. No, the difference here is that we will ask questions before picking data, like what data, what image. Let me use the medical imaging and radiology terminology. So what medical image matters for the radiologist to label? So as you can imagine, using this mindset, if I have a lack of resources, like maybe like sometimes as a PhD student, you might not even find any domain expert. What to do in this case? Even now, if you work in a company, maybe you don't have the domain experts, you don't have enough radiologists. But also, even if you work in a hospital and you have radiologists, they also have some commitments, they have some responsibilities. How can you use the time wisely when you want to work with a domain expert? So now, like imagine you have a data set of thousands of images. No radiologist would agree to label thousands of images. Like you cannot tell them that machine learning or deep learning are data hungry, so we need to label as much data as we can to get high performance. That doesn't work most of the time. So active learning here is trying to to make you move one step back before reaching that domain expert or reaching the radiologist. Before reaching the radiologist, you're making sure that each image the radiologist will label would make sense to my model and would improve its performance. And why is that? Because the model itself is what told me that those images matter or not. So you're certain. So you're not just picking images randomly. You're not picking images because you think that those images would improve my performance, but rather you're picking images because you're sure now that they matter for the performance. And as we will see in the example, those images will be in like in hundreds, not in, like, I don't want to say in tens, but let's say in hundreds rather than thousands. So if you tell a radiologist to label 100 images, 200 images, I think this will be feasible, rather than giving them thousands of images and telling them to label them. And what makes this scenario even worse is that maybe most of your images belong to some class. So if you pick those images randomly, they will belong to some class, there will be some bias, and there will not be some improvement in the performance, because at the end of the day, you're labeling the same data. You're not labeling like data that has different features. So I just wanted to, just to elaborate a bit why active learning is important and why systematically picking data is important here. So yeah, so active learning again is a systematic way to pick the medical images that matter to my AI for the radiologist to annotate. So in the past years, especially from 2011, when deep learning started to have this hype, when it like reached high performance on the ImageNet dataset, and since then, most of the machine learning community, and in particular, focused on developing the algorithm. But since 2020, some shift has started to move towards the data-centric AI, because the ideology here is that in the past 10 years, we developed many algorithms, and most of them are on GitHub. They're open sourced, so there's no issue on finding the algorithm. The algorithm is not a problem anymore. But with literature and with research, there's always some peak performance. Like if you follow the literature, sometimes there is some performance that the algorithms are not able to bypass. So the mindset which has started from 2020 and is starting to gain momentum is that let's focus on the data, because if it's garbage in, it's garbage out. If we're training the wrong, like however our model is advanced, if we're giving it the wrong data, we should expect the wrong output. So machine learning is, and here I will give the difference between machine learning and active learning. So machine learning is what we are used to, is that we have an AI application and we want to improve the performance by just feeding it more data. So by training, and if we're working with a supervised learning problem means that each image, in order for the algorithm to learn, it has to be labeled. So as you can imagine, we need much data, but all this data has to be labeled at the end of the day. So, and let alone that it's random. So that's what machine learning is about. It's a system that learns by adding more data. But now active learning, the difference between active learning and machine learning is that active learning is those machine learning systems that improve by asking questions. And those are the methods that you saw in the agenda: uncertainty sampling, diversity sampling. Those methods are the methods that would provide me with the right questions, and based on what I will pick the data, which data for the radiologist to annotate. So the difference now is that I'm not improving my machine learning system by adding more data, but rather I'm improving that system by asking the correct question, such that the data that is selected for my AI system to train on is not random, but it's improving very quickly because the data has been picked systematically. So here, as you can see, machine learning has another name. So just to make it more more related to the topic. So we're talking about active learning, but machine learning, if you're focusing on the algorithm alone, you're doing passive learning. So whenever you're picking data randomly, you're doing a passive learning. you're doing the passive learning framework. You're working on the passive learning framework. So machine learning in general, there is, of course, there are different categories here, like self-supervised learning, reinforcement learning, but just to give like the general, like to make it simple, in machine learning, we have two main categories. We have the supervised learning algorithms. The supervised learning algorithms, in order for those algorithms to learn, they have to be present with the image and the label. And unsupervised algorithms, they learn by presenting images only. But here, we're always doing passive learning because we're just randomly getting our images from the real world without any question. We go to the real world, we sample images, and that's it. So that's called passive learning. So in passive learning, so here, say that so that's now your area you're working on. Imagine that this is the framework of learning you're using. And that's the real world, like our medical images. So what you will be doing if you're working on the passive learning concept is that you'll be randomly picking data. You'll be randomly picking data and then taking this data to your AI algorithm, to your model. And passive learning, in practice, it is known that it requires a large amount of labeled data because that data is picked randomly. And if most of the data belongs to some class, you will always randomly sample until you reach a point where by mistake, by coincidence, because you're doing it random, that you have the opportunity to pick data from other classes in your data set. So that's why you're always faced with a large data set of labeled data. On the other hand, when you're working with active learning, so that's your area of working, so that's you're using an active learning framework. The way you pick data from the real world is that first you ask a question, and whatever response comes will be your data. And those are the methods that we will learn shortly about the query and how we get some answers on that query. So the data you will be picking now, the difference now is that you will be picking data for your model that is based on your question. You're questioning things, and you have a goal now because your model is involved. Your model made your question objective. It's not a subjective question anymore. There's an objective question, and you will get answers, and those answers will be the form of the data. So if you're working with medical images, the response on your question will be medical images. So those are the data that you will be using in your model. And active learning, the benefit of active learning is that you will reach a state-of-the-art performance with minimum label data. So that's the main benefit, advantage, and the advantage of using active learning when developing your AI application. So that's just like a figure that, so our AI algorithm, I will just say since the past 10 years, like I'm here, let's assume it's deep learning. Since the deep learning hype, that was a big issue for the AI algorithms, that most of the AI algorithms need a large data set of labeled data. And people who are working in the medical domain, they can understand how this is challenging. So AI algorithms have been suffering in the medical domain. So fortunately, there's active learning there. And when the machine is working with the radiologist throughout the process, this would solve that issue. So the AI algorithms no longer, and you will see that today, no longer require a large data set of labeled data to keep them carrying on with the tasks we are trying to get from those interesting algorithms, really, since the deep learning hype. Yeah. So before handling active learning to Pang to talk more about the theory, so just to recap, so that's the life cycle of an active learning framework. So you will start from here. You will start from here. You have unlabeled data. You will now give a question, and that's what we will learn today. We will learn something called uncertainty sampling and diversity sampling. Those methods are the methods that will ask the question. We will send this question to the radiologist. In the active learning terminology, it's called Oracle. So again, because so after this tutorial, maybe many of you will be digging more deep in active learning. You will be now you will be faced with some terminology. So if you find the terminology query means that this is the method by which you want to sample data from your unlabeled data set. And when you're present with the word Oracle, Oracle is your domain expert, the person who will give you the answer. So here in our tutorial, our Oracle will be mainly the radiologist. So the radiologist will give us answers and label the data. So we will have now new labeled data, but which has been systematically picked, and we will train the model, and this goes on and on until when you train your model, you find that you have reached some sufficient performance. So that's mainly when you will stop. So the matter of when you will stop, it's more subjective. It depends on the domain. And when you think that your model now gives you good performance when you test, when you run it on your test data set. But here, it's not taking into consideration your test data set. Your test data set, you can consider it waiting somewhere there. But here, you're trying to ask questions, get more labeled data based on your question, train your model, test it, and go. And this can go in more iterations, because each time you will pick data, and I don't want to yeah, you will see it in practical, but mainly here you will have thousands of images. Assuming you have thousands of images, so each query you will ask the radiologist like to pick to label 50, 100 images. So that's the amount of data you will be sending to the domain expert. So that's why we're doing it in iterations. So, and that's the good thing. And you will see that you will not need many iterations really using those methods. Yeah. So before I now carry on, so from now we will be more practical. So we'll be seeing our query part. So how we'll query and how we will get answers, and how this will affect our performance. But before moving to this section, I will handle it to Pang, who will like talk more about active learning, about the theory of active learning more. So Pang, can you hear me?
Yeah, thank you very much, Abder.
Oh, thank you, Pang.
Thank you very much. And yeah, let me share my window. Can you see my window?
Yeah, I can see it, Pang.
Okay, yeah. Great. So thank you first for everyone to come in this presentation here, and thank you for your time. My name is Peng Guo, and I work with Abder at the Center of Ultrasound Research and Translation in Massachusetts General Hospital and Harvard Medical School. So as you have already know, and Abder, thank you very much for introducing a lot of information about active learning and radiologists in the loop. That's the thing that we're majorly talking about today. So first up, we want to start a presentation with answering a fundamental question: what is active learning? I know there are probably some overlaps with what Abder has already talked about, but I will try to expand something in more detail, and I'll try to skip something which is being introduced and seems boring. I'll try to keep the presentation as interesting as possible. And Also, we will talk about why do we want to use active learning, and we will unravel the motivation and advantages that makes active learning a powerful tool in the machine learning field. And as we navigate through this journey, we will encounter some fundamental concepts in which we are going to talk about as well here today. For example, the query strategies, as Abder mentioned, we are trying to ask an oracle or a domain expert to provide the labeling, and how we are going to do that. There are three strategies that we're going to talk about today, like the stream-based, the pool-based, and also the query synthesis methods. And also, by using those methods, there are some measurements which are called the informativeness measurements that are going to be used in those strategies to query data. And also, most of people are doing machine learning, and especially deep learning nowadays. And we are going to expand the topic a little bit, talking about what are the challenges of using active learning with deep learning. And then we're gonna go to a case study where we find a really classic paper that uses active learning in deep learning. And also, we are going to end everything up with a short summary then. So first of all, I have to apologize to people who doesn't trust large language models that I firstly dumped this question to ChatGPT, which is considered the most clever language AI for now. And look at the answer. ChatGPT says active learning is a technique referring to a set of technologies where a model is able to interactively query a user to obtain label data. This user could be a person, I guess, or another information source. The key idea is to allow the algorithm to choose the data points from which it learns, with the goal of selecting the most informative instances for labeling. Well, I won't say that I'm disappointed, and it basically covers the key factor of active learning, that everything we're doing is starting from the data, but not the models. And some of you might be interested in where the idea of active learning is originated. So here is one explanation from Cornell University. So active learning methods ask students to engage their learning by thinking, discussion, investigating, and creating. So I think it basically emphasized engagement of learner in selecting the most informative information to learn from, which actually match what active learning in machine learning is doing here. And also, there are also other concepts in something like statistical analysis, the statistical query models, and also the Bayesian decision theory. There are something about uncertainty evaluations. So that could also be related with active learning. And also, to talk about the definition and meaning of active learning, we have to look at the changes in our data set size and model size in a machine learning field. First up, the data set size, we can see that is growing fast. I think most of the people in the machine learning field can feel that it is happening every day, every moment. So the increase in machine learning data set sizes has become a defining characteristics of data-driven endeavors. With each passing day, the volume and diversity of available data are expanding at a really rapid rate. This surge can be, I think it can be attributed to a variety of factors, such as like we have the digital transformation of to industries. It requires more data, and also we have a lot of cloud machines, and also we have the data-centric AI researches and everything becoming more complicated. And as we witness this not exactly exponential growth, but looks like almost exponential growth in the figure, data set transition from like a mere collection of information to a really vast reservoir of information for now. And at the same time, also, yeah, you look at this figure. It shows the model size is growing fast as well. I would say is correspondingly increased, but it's still hard to say which one causes the other side to change first. It's like a chicken and egg problem. But we have to admit that the surge in model size enables the machine learning algorithm to handle the vast and big data set growth within these neural network architectures. They probably stimulate the changes in each other simultaneously. And as we see all those changes, increases in data set size and model sizes, and we have to ask us a question first. Do we really need all the available data to achieve satisfactory results? And is the utilization of an exceptionally large model necessary for our objectives? Data quantity is important, but meanwhile, data quality is also a crucial factor in the field of data science and machine learning. So both aspects play a significant roles in determining the performance, reliability, and generalizability of the models. So that's why active learning comes into play. So the primary objective of active learning and machine learning, as Abder has already introduced, is to optimize the learning process by strategically selecting the most informative instances for labeling, thereby improving the model's performance with minimal labeling effort. So there is an example on the right side, shows a classification case in iris dataset, I believe. So originally there are all the data presented in a figure, and then we are selecting only a part of the data set to do the classification work. And in this example, it is achieving really comparable results to the case where all the data is used. Also, in the real life, there are a lot of examples that covers the use cases of active learning or why active learning is needed. For example, we probably have a data set containing a massive collection of textual documents, or we have a video camera which captures surveillance information for a month, but only like a small chunk of it is usable or is actually interesting to the researchers. And also we have a biopsy that has 1 million files inside it, but we cannot just label all of them. But we still want to do some classification work, or we want to do some segmentation work.
Your sound broke, I think, Peng. Can you hear me, Peng? Can you hear me, Peng? We can't hear you. I'm not sure if it's only me.
I don't think he can hear us.
You can hear it? You can hear him, Charles?
No, I can't. I can't.
I'm trying to reach him. I'm trying to reach him. I think I don't want him to repeat everything. I think. I think maybe I will disconnect. Maybe that's what makes him make attention. Take attention. Okay. Okay, or I will share my screen maybe. I'll share my screen. Pang, we can't hear you. No. We can't hear you, Pang, if you can't hear you. Sorry about that. I'm not sure what happened. Just 1 second.
Hello, can you hear me?
Oh, now we can hear you. Now I can hear you.
I'm very sorry. I'm very sorry about it.
Okay.
So
That's okay.
yeah. So where I break out, let me see.
I think maybe 2 slides back.
Okay.
Yeah, where you had the list. Why do we need
Yeah.
active learning? Yeah, like the first slide there. Sorry about that, Pang.
Yeah, it's all right. I mean, I'm sorry about it. I don't know
Yes.
why it happens
Well, we
like
tried to
this.
stop you, but
Yeah,
okay.
I see the red thing was disappearing from my screen. Sorry. So yeah,
No.
so basically active learning can help us with such things such as it can reduce the annotation cost that we talked about, and also for some data imbalanced and rare events, active learning can also improve the model performance, optimizing the model performance, of course, and also it can bring human in the loop, as we mentioned before. So in this process, we can ask human experts to provide information to the labeling work, and also um, to involve human intelligence and expertise in the machine learning process. And also, of course, as Abder has also mentioned, the active learning can help in handling the limited label data cases. And also, time efficient training was, as I mentioned, so as the model size and data size says is increasing nowadays, we probably not it's probably not necessary for us to use all of them and training a really large model with all the data every time. So with active learning, we can probably query the high quality data, the most representative data, and train a more compact model to achieve a comparable or satisfactory results. Meanwhile, and also active learning can be used with transfer learning and fine tuning at the same time. So with the query, the data in active learning, we can fine tune an existing model to make it having a optimized results. So now here we're going to talk about how do we actually query the data from the data pool. There are generally 3 strategies, as I mentioned in the content. And they are stream-based selective sampling, pool-based sampling, and query synthesis methods. So first up, the stream-based selective sampling method. It assumes a continuous stream of incoming labeled data points is incoming in the model, and the current model uses some measurements called informativeness measurements, which we're going to talk about later. It uses some kind of measurements to decide for each incoming data point whether or not we should ask for a annotation. While this type of query is typically computation affordable, it doesn't take a lot of things to do. Its performance benefits are restricted at the same time because each decision is isolated and thus is lacking the consideration of the relationship between the data points. But however, it is considering and balancing the exploration and exploitation of the data, and for the pool-based sampling, the pool-based sampling is different from there is a little bit different from the stream-based selective sampling, but not much. The crucial difference between them is the latter one, which is the pool-based sampling, is selecting the optimal query sample by evaluating and ranking that data over the entire data set. For now, so now in pool-based sampling, it is considering the relationship between the data samples. And also we have the query synthesis methods. So the query synthesis method means the learner can request to query the label of an unlabeled sample in the input space, including the sample generated by the learner. So when I mentioned like the generated by the learner, we probably think about some the generative adversarial networks like GANs. It can help us to generate some, we say, fake data or synthesize the data and add them into the data set. So in this case, we have a lot more information in the data set, and it can help in training the model and in improving the performance. So, and we also mentioned in the previous sections, we mentioned like the informativeness measurements, so of which the active learning algorithm uses to evaluate a data point for annotation. In active learning, informativeness measurements are used to quantify the value of utility of a data point for the learning process. It tells for example, by which threshold of a measurement I should take this data or ignore that for a annotation. So these measurements helps the active learning algorithm to decide to select or not, with in the goal of maximizing the information gained from each labeled example. So the choice of the measurement depends on the specific task of the characteristics of the data set. So here are the major three types of measurements. So the first one is the uncertainty sample based measurements. So in this framework, an active learner queries in instances about query an instance about which it is least certain to label. So this approach is often straightforward for some probabilistic learning approaches, and for example, when you use a model for a binary classification, this uncertainty sampling simply queries the instances whose, like, for example, the posterior probability is near 0.5, and which means the model is not very sure about which class it should goes to. So for multi-class problems, the predicted confidence score or entropy is used as the uncertainty measurements as well in that case. So due to is simpler compared to the other to the other measurements. And due to this simplicity and how computational complexity it is, this uncertainty-based approach is widely adopted as a very popular query strategies in active learning. But however, it should have its limitations. For example, it could face some problem as it will cause data set have insufficient diversity. And this problem could somehow be solved in using density-based measurements or combining with other measurements as an ensemble method. So the term density-based method primarily means to the selection of samples based on the concept of a set, especially the core set. So I have a core set citation here down below, which introduced this core set meaning in the field. So the concept is primarily the creation of a core set serves as a representative query strategy, first of all. And this concept is primarily influenced by the compression principle of the core set dataset, and it aims to utilize the core set to obtain the distribution of the feature of the entire dataset. So by learning this core set, you can get an idea of how the entire dataset is looking like, and without learning extra information, which saves time and resources. So, and then the query by committee, the QBS approach, involves maintaining a committee. This is involves the comedial models which are trained on current label set, but representing competing hypotheses. In this case, there are several committee members. Usually, they are usually like models in an ensemble setup. In an ensemble setup, you have multiple models who will do the work of selecting samples, and each one of them will vote for the sample.
Or maybe your voice cut again, Peng.
Can you hear me again? Okay. Can you hear me again? Sure.
I think I will. Peng, I think maybe he got cut off. I think I will continue. I'll continue from where I reached, and if he comes back, he can start. I think you can't hear us, Peng, right? Okay. I think he's not here. Sorry about that, guys. I'm not sure what's happening today. Maybe his mic or something. But yeah, I will carry on. I will carry on like for 30 minutes and let everyone like take a break, and then yeah, we'll resume. Yeah. Can everyone see my screen?
Yes.
Great. Yeah. Awesome. So yeah. So the first two parts of the presentation was about what does the radiologist in the AI concept mean, and then we talked about active learning. So just to summarize, in one sentence, the goal of this tutorial is about how to systematically pick data for the radiologist to label, rather than randomly labeling data, randomly picking data for labeling. And this has the effect of that we can reach high performance with only a few labeled data. And in the example I will be showing you, as I mentioned before, that even with a very simple neural network, because you have used the correct data, you will be achieving high performance with even few data with a simple neural network. So let me just go back here to this framework, because that's what we will be working on in the coming slides. We will be querying the domain expert on which data we want to add to our training dataset. So now I will be talking about uncertainty sampling and diversity sampling. Those are methods that ask the correct question, and I will be explaining the concepts of each one. But after that, any data that will be added to our training data will be based on this objective question. So yeah, so let's start with uncertainty sampling. So uncertainty sampling is merely about catching those situations. If you look here, so that's an ultrasound image, and it shows some organ of the body. Now, our system, the goal is say that, and that's actually the real world example I will be showing is we want to build an AI system that, when presented with a liver ultrasound image, to tell us whether the liver is present in that image or not. So say, for instance, your algorithm was present with this image, and it gave us a 50% probability that a liver exists here, and it thought also 50% probability that there's no liver. And that's really that's the extreme example on ambiguity, when your model classifies two classes 50% each. So those samples now, as you can imagine, you have a large data set of thousands of images, but you are picking the images that the algorithm doesn't have an issue with, and you're not labeling those because you're randomly sampling data, and you might not pick those samples that look like this, that they are very confusing. So uncertainty sampling is about picking those images that our algorithm is very confused about detecting their class. So, and those images, as you can imagine, when you pick such images and use them to train your AI algorithm, those are like more valuable than images that my algorithm, from the first stage of its development, it's certain of its class. So if we go through those points very quick, so uncertainty sampling is about picking that unlabeled. So now we don't know the class. We want to send it to the radiologist to label. So that image is considered confusing to our algorithm, and the goal here is to add it to our training dataset. This, at the end, this image is considered valuable for my algorithm, and that's what we want from uncertainty sampling, is to pick the valuable information, valuable data to get labeled. Now, how does uncertainty sampling work? So now we will be more practical. So here, if we remember the first slides about the Radiologist-in-the-loop AI framework, we start with an unlabeled dataset. So here, our data is unlabeled, and our model, so that's now we're starting that's our first stages, gives us some predictions for those unlabeled images. So because now now again, we're working on an active learning mindset, not a passive learning mindset. So active learning means that before deploying the model to the real world to make some predictions on new examples that it didn't encounter before, which is the test data set, we want to train it on representative data that once it is deployed, we guarantee that it will perform well. So the model did its predictions on, did its predictions on our unlabeled data. And we want to add from that data, we want to select some data for the radiologist to label and add to our training data set. Now, the question here is what samples now from our data set here, what samples should I ask the radiologist to label? Now, uncertainty sampling, that's how it works. Say that we have a classification problem. As you know, when you train the model, eventually the model will give you a decision boundary. So that's the decision boundary of our model. So our model assumes that anything that comes to this side is considered class A, for instance, and any images that are on this part are class B. But what about those here? So that's what uncertainty sampling tries to pick. So it will say that, okay, those look good, like they're not very close to the decision boundary. So our model so far is very certain about those images, and our model is certain about those samples to which class to belong to. But those images that are close to a decision boundary, they seem very confusing to our algorithm. So what we will do in active learning, so you can imagine we have thousands of images, but we will here pick only the images that are on the decision boundary or very close to the decision boundary. So those images that are close to the decision boundary or on the decision boundary are called ambiguous images. So uncertainty sampling is about picking the ambiguous images for the radiologist to sample. So as you can see here, if we say that our total, the number of images in our data set is 4, 7, 10, that we have 10 images in our data set. Rather than now sending all our data set to the radiologist to label, we're now using only 2 images. So you can start to imagine now how much that our data set that we will be labeling will be much smaller than randomly picking data. So if we used, on the other hand, if we used the traditional machine learning, which is we called it passive learning, if we use the traditional way by just grabbing the data and sending it for the radiologist to label, we will be wasting time, the time of the radiologist. And as mentioned before, if we have thousands of images, the radiologist will not agree to label thousands of images. And if you that's if we assume that you have the domain expert available, of course. But what about if you want to hire an external domain expert? And here that will be costly. So will you send thousands of images? It will be very expensive. And the worst thing is that you're not sure if those thousands of labeled images will even be of value to your algorithm. Because here, as we can see, there's 7 of 10 images. If we label them, it's no value to our algorithm because the algorithm doesn't have an issue with assigning their classes, but those are making an issue. So now when we pick those images and add them to the training data set, we can now reach high performance, but from the outside, we just label 2 images. And that's the amount of effort we needed to reach a standard, a state-of-the-art performance. So that's the idea of uncertainty sampling. I like to repeat sometimes because maybe those concepts are new. So I like them to, I try my best to explain them simply, but I just want the idea hopefully to stick in our minds. So yeah, so uncertainty sampling is about picking the images that are at our decision boundary. In other words, that our model is very confused about assigning their classes for the radiologist to label. And as you can see, that's why it is called Radiologist-in-the-loop AI, because AI is involved and the radiologists are involved at each stage. So they're working in parallel together rather than just working on, and that was the traditional way, just adding data to the model and moving forward. Now, some more practicality now. Now, before I show you an example on how uncertainty sampling works, let me just give refresh our minds on the softmax function, because the softmax function is very essential in uncertainty sampling. So softmax is a very simple function, and as you can see, it contains merely two parts. So we have the exponentiation part, where we have the Euler number, which is 2.718 to the power of the input, and that's the numerator, and the denominator would be like the sum of the Euler number to each input. But let us take it from top to bottom to make it very, very easy. So now, just to recap, how is softmax used in our neural network? So softmax, as you know, it is merely used as our output layer in our neural network. Our output layer will have nodes, which are the neurons, and the number of neurons in our output layer will be the number of classes. So let's say we're working on a classification problem, and at the output layer, say that we want to classify between if the image has a liver or doesn't have a liver. So our output will have two neurons, and those represent the number of outputs. So that's the input to the softmax function, but you can also read it as our output layer. So here in this example, the input to the softmax function, which is our output, which is waiting there in the output layer, always will always be a one-dimensional array, which is called a vector, and that vector would contain three values. So if we have so this means you can now guess that we're working with a neural network that is trying to predict between three classes. So in the output layer, we will have three probabilities at the end. And that's how, I don't want to jump to the final result, but we will have in the neural network, in the output layer, we will have three probabilities, and the highest probability will be the class that the neural network predicted. So here, but let's focus on the function. So the softmax function will have the input to the softmax function will be a vector, and that vector will contain real number values, floating point numbers, in other words, in programming. Now, what softmax function does is that in the numerator here, as you can see, it will take the Euler number e to the power of each input here, the power of the input. So the goal of this exponentiation, and like if we want to give a reason why should we do that in softmax function, the goal of this step is that it wants to ensure that the output values are all positive here. So that's the goal of the exponentiation step. And in the denominator here, the goal here is to normalize our result, because the goal of because at the end we want the output of the softmax function would be probabilities. So that's why we need also the normalization step, because we want to produce a probability distribution. And we will see a numerical example to make everything clear. But just so as you can see, the softmax function is a very simple function. It is e to the power x, and here xi is each input coming to the softmax function, and the denominator here is the sum. So we will be taking that for each input. So here we will be taking the sum of the Euler numbers to all the inputs, and the goal here is the normalization. So for simplicity here, so say that our input vector values were 1, 2, 3, and here I want to emphasize that it shouldn't be. It's not necessary that it should be 1, 2, 3 or this order, but it can be any number. 3 might be here. It might be 0.9, any number, like any value, any real number is assumed to be here, but just to simplify. The exponentiation step, which is here, the numerator will be e to the power of each input. So as you can see here, and we will now, that's our result of the exponentiation step. So as you can see, all of them are positive. And the last step, to get the final result of the softmax function, you will take the result of the exponentiation. So here, e to the power 1 is 2.72. Now divided by 2.72 plus 7.39 plus 20, which is that when we take the e to the power of all the inputs. So we will, softmax function will do that for all the inputs. So if we have 3 inputs, we have 1, 2, 3 inputs divided by the sum of the exponentiation process. Now, what's the final output of the softmax function? It's a probability distribution. So that's just a review of what the softmax function is. So it's a function used in the output layer of the neural network, which produces a probability distribution. So here, when we look at, if you take the sum of that, it will be 1 because it's normalized. And if we want to know the predicted class, it is class number 3, for instance. And we will see now how we will be using softmax in uncertainty sampling. Yeah. So the general framework of uncertainty sampling. So when you work with, if we now we moved beyond that you want to use a radiologist in the AI framework. We moved beyond that you want to use active learning and not passive learning, and now we're going more deeper in now how to apply some methods in active learning. So say now you want to use uncertainty sampling to sample data for the radiologist to label. So this is also an iterative process, and this is how it works, and we will see an example. So if you found this flowchart confusing, I will show an example that shows each and every step how it works. But the general framework when you're working with uncertainty sampling is that the first step is for each, say that you have 10 images, that you have 10 unlabeled images. The first step is that for each image, you will give it an uncertainty score. And if you remember at the beginning of the tutorial, where I mentioned that when the process became iterative, when we said that we're not now picking random images, we're selecting the images that the algorithm is not confident about, that decision, now it was a subjective phrase at that time, like the algorithm is not certain, but here it's based on the score. It's called an uncertainty score. So the first thing is that for all your unlabeled data, you will give each image an uncertainty score, and what that score will be produced by your algorithm. Now now it's the job of our AI part. So the AI will give us an uncertainty score to each unlabeled image, and then we will order our images by those scores. So say that our scores are from 1 to 10. Now 10 means like most ambiguous. This means that the algorithm is very, very uncertain about those. 1, it means like the algorithm is kind of confident. So here you will order them. And why do we need to order them? Again, if you remember, as mentioned, this is an iterative process, and you have thousands of unlabeled data. You want to pick the most ambiguous of those data. Say that at each iteration, you want to pick 100 images for the radiologist to label. Okay, now you know that there's some images that the algorithm is uncertain about, but there's always more extreme cases. So you want to start with those. So here the second step is that after you have the uncertainty score, you will be ordering them from higher to lower. Like if you pick the top 10 images, this means that you're picking the top 10 extreme cases that your algorithm is uncertain about. So you will choose the top N of those, like top 10 of those images, and the radiologist will label those for you, and that goes it's expected to be iterative. But it's good, like if at the top, if you pick the top 50 and your algorithm performed well, you can stop. But you can, but that's the concept. Like you assign a score, you order your unlabeled images based on their score, and you pick the top of those for the radiologist to label. And let's see now an example on that. Now, uncertainty sampling, when you go to literature, uncertainty sampling is the big title, like it's the big title. But under uncertainty sampling, you will find many methods, but they are all under the umbrella of uncertainty sampling. But they are different methods of how to assign that uncertainty score. Because here, as you can see, we said that each unlabeled image has to have an uncertainty score. So here we have different methods that provide us with that number. That score will be a number, and different methods have different ways to give you that number, but at the end, it's an uncertainty score. So in this tutorial, we will be talking about a method called least confidence sampling. So as you can see now, I will go through the steps, and you will see that it's very similar to uncertainty sampling. Maybe it will go a bit detail just to take into consideration that we're talking now about a special case of uncertainty sampling. So the first step here, we compute the model's probability distribution. I think you're familiar with that. So here, we're working with softmax at this stage. So we generate the probability distribution using softmax for each our unlabeled data. The second step is we identify the maximum value in the distribution. And I will show an example now, but I'm just going back just to show you what you are familiar with so far, but I will show now each step in real world examples what it will show us. The second step is to identify the maximum value in the distribution. So that's the maximum value in the distribution. It's very simple. So I have the probability distribution, identify the maximum value. So here it's 0.67. Normalize the maximum value. Now, because we will have more than one unlabeled data, we want all to be from 0. We want to ensure that all are from 0 to 1 and that are relevant to our data set. And I will show you the equation that we will be using for that. And finally, we will get our uncertainty score, so all of that is encapsulated here. So we got our uncertainty score, and at the end, before moving to the radiologist to label our data, we will select like the top 10, the top 50 with the highest least confidence score. You can like think about it as our uncertainty score. So we will do that for all our unlabeled data, and that will give us an idea of how now to systematically pick data from our data set for the radiologist to label. So now we are picking the top, like the top N images that are confusing our algorithm for the algorithm to label rather than randomly. Let's see this in action. Let's see this in action, but let me give you a break. Because let me give you a break. We can take a 15 minutes break if everybody's fine with that. And we will see a real world example about how we can use uncertainty sampling and diversity sampling, active learning in general, to develop an algorithm that would classify our images by telling us, does this image contain the liver or not? So yeah, we can have just a 15-minute break, and yeah, we resume our tutorial. Thank you for your patience, everyone. So we can resume, everyone, if that's fine. Yeah, I think we can, yeah, just continue. Yeah, so thank you everyone also for all your time again. I really appreciate your attending. I know everyone has a busy schedule, so your attending is really, I really appreciate it. So, so here we will be now seeing some real-world examples about how to sample data in a systematic way for the radiologist to label. Now, we will start by showing now, we explained the concept of least confidence sampling, but we will be now seeing every step, like how every step is calculated and how it looks like as an output. Like how does the model probability distribution look like? What happens when we identify the maximum value, normalize it, and eventually how we reach that score. So that's the main thing I will be showing, because that score is now the objective score, which will tell us as machine learning researchers how to pick which data to pick for the radiologist to sample, to label. Before moving forward, the good news is that anything I will be explaining is provided in code. So the code I used is open sourced. So you can if you go to the Radiologist in the AI loop, the Radiologist in the loop AI page, if you go down, you will find a logo to GitHub, which will take you to the same page. At the end, towards the end of the tutorial, I will walk you through the page, but just to mention that anything you see is implemented is just about using your data for that, but each step is explained in detail, like how to organize your data, from how to organize your data to how to run each concept we are explaining today. So don't worry about how you will take it from there. So yeah, so the good news is everything has been implemented. Yeah, we will come back to this page later on. So let's now see how least confidence sampling works on this problem. So now, again, we want to pick data for the radiologist to label. How we will pick this data. So the first step, as we mentioned, compute the model's probability distribution. Now, when we see probability distribution, it's the softmax job to do that. When we explained softmax, we saw that the output of the softmax is a probability distribution. So here, so that's like a sample of my data that I used. So I had like many images, but I'm just showing here the output of the softmax. So you can imagine you have a neural network. It's implemented, so don't worry. Everything is implemented. So in the output layer, we have two classes. So if we come here to the equation again, this input will be A and B. So because we know that softmax is represents our output layer, so the number of nodes will be the number of our classes. So here we have two nodes in the output layer. One node will be related to class 1, which is the class that tells me if the liver has the liver, if the ultrasound image contains the liver, or if the ultrasound doesn't contain the liver. So that's the output of my softmax function for each input. So if we say that we have, so each row here represents one unlabeled image. So the first step is that we want to find the probability distribution. So as you can see here, we have the probability distribution. And since we are now at the beginning, this is expected that, as you can see, our model at this stage is very confused. Look, like it's 50%, 48%, 20, 40, 52%, 48%. So in other words, it is from this figure, we can see that it's kind of giving a probability for each image that, like each class the image belongs to, has a high probability, and that's normal and expected, especially first. Now, as I will see, you will see in the coming examples, I started with two images, with two random images to label as my training data. So my training data set at this stage is only composed of only two images, and they might belong, it seems they belong more to this class. But yeah, so we're starting with a small data set. The data was randomly picked, so it's expected that my algorithm is still confused. So that's the first step. We have the probability distribution ready. The second step, let me go back, identify the maximum value in the distribution. That's very straightforward. So here, so that's the second step, identify maximum value in the distribution. So at least for this screenshot, because they're not in order, so that's like the output of the different images that were coming in the neural network. So that's, so most of the maximum values are here. We're just following the process. Then we normalize the maximum value. So that's the equation used to produce images that are from 0 to 1, which are relevant to the number of labels we're working to, because we want to have them the same weight. So that's the goal of the normalization. So we have 0 to 1 values in relevance to our data set. And the final step is to compute the least confidence score. Now, the normalized value, so the result, in other words, the result of the normalization equation is my least confidence score. So this means that for this image, for instance, so that's now the difference now. So we have an input, but now this input has a confidence score. So we started with an unlabeled image, but that unlabeled image, based on my algorithm, is telling me that the uncertainty is 96. The uncertainty score is 96%. Now, the higher the value, the less confident our algorithm is about. So that would be a candidate. That image with such high uncertainty score is a candidate for me to send it to the radiologist to label. So here, let me just see where we are at. So we performed the blue boxes. So we performed the first four steps. We got an image as an input, but this image now has an uncertainty score. Now, for instance, we have thousands of images. Now, each image is assigned an uncertainty score, but we don't want to send all of those thousands of images to the radiologist. We will be selecting the top 10, top 20, as much as you like, that you think are feasible for the radiologist to label. So for this orange box, that's the result of this orange box. So we now order our input unlabeled images based on their uncertainty score. So as you can see here, the top is the most uncertain. So as you can see, the values are close, but when you're limited with the in the domain expert part, like you are limited with the amount of images you can pick for the radiologist to label. Like even if you have some images left that are still confusing the algorithm, at least you're starting with the extreme cases first. And those extreme cases, when I show the results now, you can see that they really matter sometimes. Like they would make our algorithm more confident, such that we will now have less of those extreme cases. So we might be we will get some uncertainty scores, but we will start to see some less values than 0.97. So those are very extreme. One means 100%. So that's the extreme case of an uncertainty score, and the 0 means that's the most kind of image that an algorithm is able to classify confidently. But here, let's just walk through the steps of the algorithm as is and see where we will reach in that. So yeah, just a look again. We found the probability distribution of the inputs we have. So we're assuming here that our inputs are unlabeled. So here, as you can see, we have some metric to tell us which images to send for the radiologist to label. So now we have a metric. So those are unlabeled images that we didn't label, we didn't show the radiologist, we didn't use it for training even. But it's for us to decide which of those we can use for labeling. So there's a probability distribution calculated, and that's done using our neural network. So in the implementation on GitHub, that will be done for you. All of those steps will be done for you automatically. So we have the softmax producing the probability distribution. We're picking, now we're just following the algorithm. That's it, very simple. We're identifying the maximum value, normalizing the value, and that's our uncertainty score. Then we order those uncertainty scores because I'm expected to work on it in iterations. So at least at each iteration, I am picking the extreme of those. The highest uncertainty scores are the most extreme. So now in GitHub, you will find that I provided a very simple convolutional neural network. And I did that in purpose to show you that even with a very simple architecture like that, which is composed of 2 convolutional layers. So those numbers here show you the number of filters, the number of outputs to that layer, and the number of outputs. So those are the numbers, and in max pooling, the number of the kernel window, because in max pooling, there will be a window. So this means that these are 2.2 window passing through the image. So, but anyway, those are just to make it more accurate. But the implementation you will have has this architecture. So as you can see, our problem is not easy. Especially, remember that we want to do it with a very small amount of labeled data. And that problem is related to images that are known to the community that are very noisy, ultrasound images. So it's not a simple problem. The images are challenging, they're noisy, and we want to tell from those noisy images whether they contain the liver or don't contain the liver. And the challenge here is that we want to try to do it with a very simple neural network. So as you can see, it's just composed of 2 convolution layers and 3 fully connected layers. And but let's see how it goes, and that's the goal here. Let's see, there was no intention that I want. I'm just presenting here the outputs I got as is. Like, I didn't want to make the results fancy and try to convince you that active learning is better or not. I'm not trying to convince anybody here, but just to show you the effect, especially when you don't have the domain expert, or you can't label thousands of images at the end. So that's the goal here. So let's see how it went with a very simple neural network trying to solve a challenging problem. Yeah. So our problem here is a supervised learning. Our algorithm is a supervised learning algorithm, which means that each image that has to be fed to the algorithm, it should be labeled for the algorithm to learn. So that's supervised learning. It cannot learn without a labeled image. So if you go to literature, especially deep learning, and that's like a deep learning algorithm, but it's like because it's a convolutional neural network, but it's not that deep. You can see it's shallow, just two convolution layers. But I wanted to put this slide because if you go to the deep learning literature or if you're reading some textbook, it will tell you that supervised algorithms are data hungry. And that's true. So when I started, like when I first encountered working with deep learning in the past, like the first thing I learned is that where's the data, where's that huge data that I need to feed my algorithm? And they always mention that the more data you have, the better performance you will get. Okay, that's true, but how will I get that data? That question was started to raise when I started to work with them in the medical domain, and where most of the time I don't have someone to label the data because I need a domain expert. I cannot label all that data by myself. And even if I want to label it by myself, how much images can I label? Like either I would put time to, so that time, the trade-off was that either my time and effort is put in model development or in data preparation. And I had to choose one of them. But active learning can narrow this gap. It can narrow this gap by you can focus on your model, but on the back of your head, you know that if I want to label data using this framework, I will not need thousands of images to reach high performance. So again, we're working on a supervised learning problem. If we now go back to literature and textbooks, we are assuming that not only my architecture would not work, but if I want to make it work, I need thousands of data. Let's see if this is true or not, if using uncertainty sampling here. So here, this slide shows an example of the two classes we are working with. So here are this data. Those are examples of images that contain the liver. And those are examples of images that don't contain the liver. So those are the kinds of images that will be labeled. Now, here I will show you the outputs I got through the different stages of uncertainty sampling. So I started with my training data. At the first, in the first iteration, it was composed of two images only. And here I was a bit, I didn't really pick them randomly because they are just two images. So I just wanted to make sure that each class contains one image. But in the real, but the real way to do that is that those images have to be picked randomly, because especially when you're working with some images that you don't know the output, like you don't know that this is the liver, that you don't know this contains the liver, this doesn't contain the liver. But I just wanted to start just to make some, to avoid the issue of data imbalance here, just to start with a balanced data set. So here, that's how I started. That's my training data. And that was my accuracy, test accuracy. So I had some test data waiting to test my algorithm, because that will be telling me when to stop, because that's my, like at the end, my the metric I will decide based on when to stop labeling more data or adding more training data. So as you can see from the first iteration, the performance was not good, and it's expected. So it's like a chance. It's like even less than a chance, because if you're doing that by chance, it will be 50%. So it's 46%. So now let's apply uncertainty sampling. Here, as you can see, so I'm putting everything together. So this part and this part, that's our first step, the probability distribution. So that's the probability distribution. And using the equation, the different steps, we will have the uncertainty score, which is we're using the least confidence sampling, as you know, but let's think of it as our uncertainty score. So here I just put a snapshot of the top 15 images with the top, which have the highest uncertainty scores. So as you can see, we're almost 100% for those images. And in my data set, I put the lower 15 of those. So as you can see, there's no point of picking those images for the radiologist to label. So those are 15 images, and those are 15 images. They will take the same amount of time from the domain expert, the radiologist, to label. But if we pick those, our performance would not differ that much. Although we added another 15 images to our training data set, but our algorithm is telling us from the beginning, using only 2 images, it can predict them like confident in a very confident way. So, but picking those can make a difference. Our algorithm, because now things are becoming more objective, we're not random anymore. Our algorithm is like telling it loudly by those high numbers that I'm not confident about predicting that image and that image and that image and so forth. So you can see the difference here. So now say that our first iteration, we wanted to pick the top 15 of those. So so those are literally the steps I mentioned. So we pick the top 15, for instance, or top 50 for the radiologist to label. Now let's see the effect of that. Now those are samples of the top 50 images. So when I was preparing the slides, I picked 50 images and I picked some random samples. So those samples are the images that gave me those uncertainty scores. So the algorithm was like, maybe when I showed you the samples at the beginning, you said, this contains a liver, this doesn't, but like we're now talking to a machine. So now we're using the machine to tell us that. The machine would not think like us, but involving the radiologist, the effort of a human and a machine will be more fruitful because we're doing that in parallel. So those are 4 samples from the 50 images that I selected for the radiologist to label. So now we're doing uncertainty sampling. So we pick the first 50 images in here, the first 50 based on the uncertainty score. So that's what first 50 means. This means that the first 50 extreme cases. So we might have like 9, 6, 8 after that, but like those, we're picking the top, the top extreme. We can't pick all the extreme cases at this stage because this will differ. Now we will get different results because those ones that were not confident in that stage, adding the images that matter, which are picked systematically, might make the algorithm will reduce this number. So this number will not be the same. So for instance, that image here, if it was not picked for training, of course, it will no longer have this. This number is a variable that will change based on the new training data, based on the confidence that the algorithm is gaining. So that's why we're picking like the top extreme here. It's not that there's no other extreme cases from the 50, but we're taking those top, even if the difference is few. So yeah, so here we picked the top 50 images that are with the highest uncertainty scores, and we gave them to the radiologist. The radiologist will label them, and both parties are happy. The machine learning researcher is happy from the fact that he or she are certain that their images that will be labeled are of importance to the algorithm because the algorithm told us that, and the radiologist is happy because 50 images, he would tell no problem. The radiologist will do them very quickly. So both parties are happy. Now, moving a flash forward, so this will be done at different stages, but let me show you the effect of uncertainty sampling. So I started with 2 images. The accuracy was 46%. I then added 50 images, but those 50 images were the top 50 extreme cases, which top 50 uncertain images, but they were extreme from the fact that we saw that they have the highest uncertainty scores amongst the others. Now, using 52 images, now using 52 images, let's remember that we're using a very simple classifier. It has only two convolutional layers, and I will just want to go back a bit, and those layers have very few nodes. It's just 6 nodes. Like, it's not like big layers. It's not like, in other words, that's why I called it a simple classifier. Even in GitHub, I called it simple classifier. But this simple classifier was able to deal with a challenging problem using 52 images, which we learned before, that such algorithms that are supervised are data hungry, and that was mentioned about the advanced neural networks. Let alone a simple neural network, what can it do with such a problem? But now we can see 52 images, 71%, 102 images, 85%, and so I just stopped there. You can continue, but I'm expecting that maximum, like maybe we're dealing with a challenging problem, we're using a simple classifier, we might end up with labeling only 300 images to get a state-of-the-art accuracy. So here, using 152 images, we got 87%. And let me give you a more meaning to this number. So this year, I published a paper at CVPR. This paper was about the same problem. It used liver view classification. Now, I used the MLP mixer. So there's an architecture called MLP mixer developed in 2020 by Google. MLP mixer was trained. I don't remember the exact number, but on top of my head, it was around 900 images. So 900 images, and I needed to label 900 images, and I fed those images to a very, very advanced architecture. It gave me an accuracy of 87%. So that's the most I could achieve using labeling 900 images. Here we're talking about 152 images with a simple classifier. When we're saying simple, this means that also the hardware requirements are different. MLP mixer is a very advanced algorithm that it really took much time, sometimes for days, to train on a GPU. Here, this simple classifier, it might work with a CPU. So in other words, you can use it in real time, in a real-time setting. Like if you're using it with a machine, with an ultrasound machine, for instance, it's in real time. So in a real-time device where you don't have that hardware resources anymore. This problem also, I used ResNet 18, which has 18 layers, a convolutional neural network with 18 layers that the community has been using for a while now. And then they started using ResNet 50 with 50 layers. The most I got, and maybe I really used ResNet 50, I really forgot if I used 18 or 50. The most I got was 73% for this problem, by labeling 900 images. So I think picking the right data matters from what we can see here. So what if we had an advanced, the question here, what if we have an advanced algorithm, which now it's not hard to obtain, and that's what I mentioned at the beginning of the tutorial, that from 2011, let's say in the past 10 years, no one now is short from using an algorithm. It's all on GitHub. It's all open sourced. But the challenge and the data-centric AI has been gaining more momentum since 2020. because it says that models are available, but they can reach a limit in their performance. So the shift is becoming slowly towards data. And in this tutorial, I wanted to show that this shift is for a reason. It didn't happen coincidentally, or it's just, you know, we are fed up with model development. Let's try another something else. It's not that way, but because researchers started to realize that data matters. And that's an example. I will show another example using diversity sampling this time. So that example was used uncertainty sampling. Uncertainty sampling, as we mentioned, selects the data that is on the border. Let me just show this figure again. So uncertainty sampling picks the data that are near our decision boundary and tells us that those data is the data that you have to pick for labeling. Other data doesn't matter, and the model is telling me that. So you might use if you're working with a segmentation problem, you might use UNIT, for instance. You will do the same approach when you use uncertainty labeling. Your model, your algorithm will differ. Here, I provided you with a classifier just to show that that even if your neural network is simple, if you focus on your data, you will gain high performance. But this applies to any model you use. So even if you're using some advanced models, which is good, but now even for those advanced neural networks, sometimes they need thousands of images. And I gave you an example about ResNet, how it with 900 images, the most it could make with this problem is 73%. Yeah. So I will the next part will be using the same concept, but now the same concept of systematically choosing data for the radiologist to label, but this time it's called diversity sampling. So uncertainty sampling means picking the images that are at the decision boundary of the algorithm. Now we will see what diversity sampling in the coming slides, and they can be combined. If you like, we can just take 5 minutes break. I know maybe your minds are loaded now with much data, but I will just stop for 5 minutes only because we will conclude in less than an hour, but just 5 minutes because this will be another concept now. But I promise I will keep it short, especially that you have all the code, as mentioned. You have all the GitHub code, all the details. But after the tutorial, if you have any questions, please feel free to reach out. We can. My email is there, and also on GitHub, the discussion on GitHub, we can also take it from there. Yeah, I will just 5 minutes break and we'll resume on diversity sampling. Thank you so much, everyone, for your time. Hello everyone. Yeah, we can resume. So thank you for waiting. Thank you. Yeah. So we talked about how uncertainty sampling works, and we saw that it is a way by which we ask the algorithm or your AI model that you're working with to I'm opening. Yeah, I'm opening the mic. I just want to make sure that I'm opening the mic. Yeah. So it is a way. Uncertainty sampling is a way by which we, based on what our AI model told us, it's a way that when we want to get data from the real world, we are getting that data that our AI model was a bit confused about, that it wasn't certain how to deal with those images. It wasn't certain how to say that this image has the liver. It doesn't have the liver. So uncertainty sampling is about picking those confusing cases. So you can remember it that way. So when you're talking about ambiguous cases to our model, confusing cases, we're talking about uncertainty sampling. Now, we will move to another concept in active learning. It's called diversity sampling. The concept, what is similar here, when I say the concept is similar, the concept of systematically picking data. But now, diversity sampling will be asking another question. It's not looking at the confusing cases. It's looking at something else, which we'll learn here. And I want to mention here that you can combine those together. So you can use uncertainty sampling with diversity sampling. That it's not necessary that if you use uncertainty sampling to pick your data, you cannot use diversity sampling. You can make a combination of those. So similar to the figure we saw earlier about the decision boundary that our model gave us for a classification problem. So let's say that let's say that using the names that we use in this tutorial. So the simple classifier is trying to tell us if an image contains the liver, so with liver, that we call this class with liver, or without a liver, without liver. So that's our simple, after training our simple classifier, that was the decision boundary. So here, we want to use diversity sampling. Now, if we wanted to use uncertainty sampling, we will be looking here at this line. So we will not see it in visually, of course, but the algorithm, like mathematically, as we saw in the method we saw, that the method is trying to focus on this part. So it's like we're focusing on the decision line and trying to pick anything clear. So it's like a danger line here. Like if the more closer the samples, those are the ones we want to pick. Diversity sampling is different. So the diversity sampling it goes to each class. So let's say that we're now in this area. It goes on the samples that are far from like how the data set is grouped. Now, if we want to use some distance, like Euclidean distance or Manhattan distance, if we measure the distance between the features of those images, they will be very close to each other. So this means that they really belong here. They really belong here. Like they belong in this class, but they're similar. Because at the end, if we're training our classifier to give us two classes, it would produce a result. Even if there were some images, say that I had an image, not a liver image, say that I had maybe a natural image, it will belong to some class here, because that's the job of the algorithm. It should, you told us that you told that algorithm that I want you to classify my data into two classes, so it should at the end put all your data in either of those classes. But some data might, although they belong to one class, they're a bit different. So, but here we're assuming that all our data was ultrasound data that contains some organ, abdominal organ in particular. but we want to see if it shows the liver or not. But what diversity sampling focuses on is that it tries to pick images that are not far from the decision boundary, far from the other images. Those are called outliers in active learning. Those are called outliers. So, which means that if you want to see the features of those images compared to the features of those images, they shouldn't belong here. But where else? There's no other class because we're classifying two classes. But here, those images are not necessarily images that are not abdominal images, but they contain some features that the algorithm couldn't deal with. Like, even if it assigned it to a class, it's like they don't belong here because maybe they had much noise, maybe they had some, based on the scan, maybe they had some artifacts, things like that, that made them very far from the images in the classes. So I will show the same thing, that some examples or some real world examples using abdominal ultrasound images and how the effect was in performance. But the idea here, as again, is that diversity sampling is trying to pick data which is far from other data in its class, and that's why it's called diversity, because it's trying to pick some rare cases. So if you're working on a cancer classification problem, let's say that you're working on, you want to classify like if some patient has, let's say like skin cancer or not. Now, you have a large data set. It's a good data set, but there are some rare types of that cancer. So it's different from, like, it's melanoma, say it's melanoma, it's skin cancer, but it's like it's a rare case. So it's diversity sampling is trying to pick those rare cases to include the different situations you as a machine learning researcher or or someone who is developing an AI application that will be deployed in the real world. By doing this by using diversity sampling, because when you're training your model, you can't contain all the cases you have in the real world. But here, picking those outliers, those rare cases, at least you can rest assured that your model will perform well in the real world, even if rare cases popped up and were like used in your model. So that's the goal of diversity sample, to try to include as much samples as we can. Yeah. So again, as we reviewed softmax, because softmax, as you saw, was essential in working with uncertainty sampling. Here, I will give a very quick, like, refresher, or maybe if people are not aware of k-means, I will explain it very simple. So, to know what the k-means clustering means, because the reason for that is, in literature, when you want to work with diversity sampling, most methods that are used are called cluster-based sampling methods. So k-means is an example, fuzzy c-means. There's many clustering algorithms. K-means is the most used one, but you will be encountered with this term, with this phrase, because a cluster, the idea, before going deep in what k-means is now, the idea of cluster-based sampling is that instead of randomly picking data, so now put aside the uncertainty sampling. We're starting like from the beginning. We have unlabeled data, but we don't want to pick data randomly. So cluster-based sampling means that instead of picking data randomly, we divide our data into different classes. You can assign those classes. Those number of classes are different from your output. So in our example, our output is, we want to the algorithm to classify if we have the liver included or not. Now, here it doesn't it doesn't do with your model's output. Here, it's merely dealing with the data. It's merely dealing to make sure that you can contain all your data, regardless of if there are some rare cases or there are some cases that belong like outlier cases. So, for instance, here, if we look here, we can say that we can like the number of clusters. There's no fixed number. Like you can try any number, but if you think that your data might include like different cases apart from the most common ones, you can say that if you're using cluster-based sampling, you can say that I want to cluster my data into 5 classes. So 5 is not what our algorithm will produce, because here we're not focusing on what our algorithm will produce. We're focusing on how to sample data. So that's why. So here, don't confuse the number of clusters using here with the number of outputs. Yeah. So the goal here is when you put your data into different classes, the idea here is that when you want to sample data, you will pick the same number of samples from each class. So here you can make sure that you included the different cases in your data. So say, for instance, you wanted to pick 10 images for the radiologist to label. Say that you had 5 classes, you will take 2 images from each class. But when you do that, since you put your data in 5 classes, when you do that, you make sure that you included different aspects of your data. Like even if your that solves the issue of the bias here, because say that you have 1,000 images, 8,000 images belong to say that most of your images, like 800 images, belong to one class. If you randomly select from that data, most likely you will always get images from that class. So there will be some bias. So your model will perform very well on that data, because most of your data that has been trained was from that class, and you're leaving out other data, especially if the rare cases were like 5 cases from 1,000. Most likely you will not even train your algorithm on those images, because what's the probability of picking those 5 images from the 1,000 if you're doing that random? And no wonder why, when you deploy your model in the real world, if it was presented by such cases, it didn't perform well. And you don't know you have the data. Like you have the data, but when you have thousands of data, you cannot look at each case and pick manually. So that's the goal of cluster-based sampling, that one aspect you can pick from the different data based on their features in your data set, because you put them in classes. And for the outliers, I will show you how we can calculate that. And again, everything is implemented, how you can pick those outliers, because you have 5 classes, but you also want to pick the outliers of each class. And see, by this way, you make sure that your samples that you are labeling, you are in one way or another picking each aspect of your data. And even if most of your data had one class, this way, you know that even the rare cases, you're picking them. So your model eventually, and that's the goal of active learning, your model will perform well using a small amount of labeled data. So let me just give a quick overview of what k-means is, and then we will see an example of diversity sampling. So k-means clustering, as you can see, assume those are you have 7 images. Now, as an image, it will have many features. Yeah, like it will not have 2 features. Like even the pixels, like the number of pixels, each pixel would be a feature. So if you have 100, if you have a 100 by 100 image, you will have 1,000 features. But for simplicity here, like to demonstrate, let's see that your image has 2 features each. So each image is represented by 2 features. The first step in k-means is that you will here we have 2 dimensions because we have 2 features. So you can put feature 1 on the x-axis and feature 2 the y-axis. It doesn't matter. But let's see here. Let's see, like feature 1 can be here. It doesn't matter. But let's say that we had this order. The first step is very simple. So it's just about a matter of plotting those points on a higher dimension. So sample 1, feature 1 has the value of 1. So that's the value of 1. So it's just XY axis, like a Cartesian plane, very simple. And feature 2 is 1, so 1, 1. For instance, this one, so that's called point 1, so I just labeled it 1. 4.4, 2.75 will go to the x-axis, so that's 2.75 around here. And the y-axis 1.25, 1.25, so that's 0.4. So we will do all that for our samples. So we plot our samples on the plane. Very simple. The second step is, it's called k-means. K represents the number of clusters you want to classify your data in. Now here, let's say that we want to classify those points into 2 classes, which means that class 1 will contain points that are more similar to each other, and class 2 will contain the points that are similar to each other but are different from this class. So here we said that we want our data to be grouped in 2 classes. So if this data was class 1, this means that they are different from this class, so they don't belong here. So they belong to this class. You can name this class. Let's say that those are the liver images. So, and those are the non-liver. So that's what it means. So we want our algorithm to k-means. Now we want to start with 2 clusters to group our data together. Like data that is similar has to be in 1 class, and they have to be different. If they're different, they shouldn't belong to the other class. Now, the first iteration, we start with a random initialization, which means that we will pick randomly the center of our data. So the centroid, or it's called centroid in k-means. The centroid means it's the center of our cluster. So that would represent the center of our cluster, because when we want now to find the distance, as I will show in the next slides, that will be our reference. So we will take the distance to that center, and based on that, we will say that whether the sample belongs to that class or not. So the first step is to pick the center. So let's say that let's say that our first sample is our center for class 1. So let's say that class 1 had this. Maybe it's not correct, but it's just something to start with because it's random. So that's our the center of our first class, and that's our center of the second class. And so those are our centers, because we have 2 classes. The third step now is we use Euclidean distance. I mentioned before a while that we want to find a distance, but distance between what and what. So let's say here, that's centroid 1. If you look here in bold here, that represents the features of our center here. 1 is 1, 1. So this is the x-axis, and this is the y. So here, so that's the x. So you can, so that's the equation. As you can see, the first part of the equation are the x-axis, and the second equation is the second part is the y-axis. So x here, because we're now in centroid 1, we have all 1 in the X, because it's 1, 1, as we saw, and Y is 1. Centroid 2, before, like, without looking here, or if you look here, you would guess that X feature 1 has the value of 6, and feature 2 has the value of 2.5. Let's check. Look, I said so. Since I said, yeah, feature 6. So feature 6. So 6 here, that's our X, and 2.5. So 2.5. Why are those fixed here? Because those are our centroid. So that's our centroid from which we want to take the distance from each point to the centroid. So what this part is telling us is that I want to find the distance from 3 to 1, from 4 to 1, from 7 to 1, all the points to 1. And that what this part is telling us is we want to take the distance from every point to 6. So when we take the distance now, so this one is a distance from 1 to 1, because we're taking each sample. Now 1 to 1 will be 0, as you know. It's like, it's the same point. If we take sample 2, so sample 2 here is, sample 2 here, what's the dimension of sample 2? 4.5, it's 4.5, and the Y is 4, sorry, it's 2.5. So we can see it here more clear. So sample 2 is 4.5 and 2.5. So what we'll be doing here, the same thing, we will take the distance from this point to this point using Euclidean distance. So that's the distance. So it's increasing, as you can see, and from visually it's really far. The same thing. Sample 3, we take the distance from 3 to 1, it's 1.12, and so forth. We will do the same thing, but this time, if we take the first sample, sample 1, from 1 to 6, look at this distance, 5.22. It means far. So we'll do the same thing, but now taking the distance from each point to this centroid. Now, that represents our first iteration. What are those boxes I highlight here? The boxes here before moving to the next step, because now the goal of this step is that the first time I started my k-means, I picked the centroids randomly, but now I need to pick the centroids mathematically and not random. So those highlighted ones, what we do here is we will check. Now we will make a comparison, like larger or smaller, very simple. Is 0 larger or smaller than 5.22? Now, the column where the value is smaller means that this column, this value belongs to the cluster it is under. It is like in other words, if the value is smaller, like sample 1, wherever you find the smaller value, this means that gives you an indication which class you should put it in. So if 0, since 0 is less than 5.22 and it is under 1, it will belong here. Here, if you look here, 1.50 is less. So you will, in other words, you will be looking for the minimum value. And where did you find that minimum value? So that minimum value was under class 1, so it will go to class 1. This minimum value here, it's under class 2, so sample 2 is telling me it will belong to class 2. The same thing, 1.12 is the smaller one. Where did it come under? It came under centroid 1, so it will go to class 1. So here the rectangles you see here are highlighting which samples belong to class 1 based on the comparison of the distance of each one, and which sample belongs to class 2. So using this, the first iteration told me that 1 and 3 and 4 will be grouped together. And it told me that 2, I'm following the boxes here, 2 and 5, 2 and 5 and 6 and 7 will have their own class. Moving to the second iteration, we will now calculate our new centroid. So our first centroid was 1 and 6, but that was calculated randomly. So calculating the new centroid is very simple. We will take the x-axis of all the points here, the x-axis of all the points that belong to class 1. So it will be 1, 2, and 2.75, as you can see here, divided by 3 to normalize the result. And those are the y-axis for those points. And cluster 2, the same thing. This shows the sample numbers, and here it shows the sample dimensions. So class 2, we had 4 samples. We're simply taking their x-axis and y-axis and producing a new centroid. So as you can see here, now centroid 1 has the dimensions 1.92 something here. It will be something here 1.92, 1.25. So that will be the location of our new cluster, a new centroid for that cluster. And here you will have a centroid somewhere here, because again, why do we need a centroid? Because when we want to find the distance, it gives us an impression on where to group our data. Now, how do we end k-means? That you will do the same steps by finding the Euclidean distance from each point to that new centroid that we got in the previous step. So that's our new centroid now. The same thing. So here you can see 1.92, 1.25. It's fixed because that's our first centroid. And here the same thing. We take the Euclidean distance from each point in your data set to that centroid to produce the distance. And the same thing, we will take the minimum of those. The minimum, if the minimum was under class 1, it belongs to class 1. If the minimum was under class 2, it belongs to class 2. And since nothing changed on how our data is grouped, so in the previous step, 1, 3, 4 belong to that class, and 2, 5, 6, 7 belong to that class. And here, k-means tells us to stop. And that's the criteria on when to stop in k-means. It is if you worked on 2 consecutive steps, the result didn't change. So yeah, so that's k-means. It was brief and not brief. I know it took some time, but yeah, I will, considering time, I will jump to the results immediately. So here I am using, everything is implemented again. So all of that and applied on the data is implemented in the on GitHub. So let's see the effect of now using diversity sampling on our performance. So the same thing, I started with 2 images for our training data. Those are different images from the ones I started with in uncertainty sampling, and just to see if what happens. Like, there was no purpose on using those images. They were literally used randomly, but maybe not the random thing here was that I wanted to make sure that the image belongs to, I had 1 image per class to avoid imbalanced data at the beginning. So we started with our simple classifier. So we're using the same classifier to solve this challenging problem. But now we're using a different way of how to sample data for labeling. So starting with 2 images, we're now around 56%. We need to improve that. Now, we're doing now k-means cluster sampling. Here, as you saw, and as mentioned before, the first step in cluster-based sampling, we want to group our data in different classes, because we want to make sure that when we sample data for the radiologist, we have the different aspects of the data in our data set, rather than picking the data with the most, like maybe most of the data belong to one class, for instance. So here we applied k-means clustering, which I explained before a while, to group. So here those are samples. So if you go here, you can imagine those are our images. So yeah. So here I said I used k-means clustering to group the data I have into 5 classes. So as you can see here, I provided a sample of each class. Now this is the number of images in each class. And so here, as you can see, most of our images belongs to 255. And as I told you, I just wanted to show you the results as is and the data I worked as is. But in some situations, maybe imagine that you have 1,000 images here, and here you have 2, 3. Most likely, when you randomly select, you will be selecting from only one aspect of your data. But as you can see here, yeah, like k-means is doing well, really. Like if you look visually, the group data have some similarity in some aspect or another. Like k-means, as you saw in the explanation before a while, it uses features of the features of the images to group them together. So based on the k-means algorithm, that's how it grouped the data, and that's why k-means is performing well, I can see. So that's the first step in cluster-based sampling. I put the data into classes. I picked 5 classes without any. I just picked it randomly. Like I picked it randomly. Yeah. So the first step in diversity sampling is that I will randomly, but here don't mix randomly. We said that in this tutorial, we're no longer picking our data randomly. But here it's telling us to pick randomly from the different classes. So it's like it's more narrow here. I'm picking from each class randomly, but the criteria here is that I need to pick the same amount of images. So if I pick, sorry about the mouse. I will put my hand away from the mouse. So here, if I pick 3 images from this class, I will pick 3, 3, 3. So here it's telling me randomly, because here I have 166 images. When I pick 3, I can pick any 3, but I have to make sure that from other classes, I have to pick the same amount of images I picked from each class. So randomly and evenly sample data from clusters. So that's the first step. The second step is, remember when I explained k-means, there was a centroid, the center of the class. This cluster-based sampling tells me, okay, you picked like 3 samples from each class, pick the center of the class. The center will be only 1 image. So that's the center. If we want to take it like, what does the center mean? Away from the formal terminology, the center is a sample which represents all the other samples in your class. So it's telling me, apart from the 3 random picked images, give me the center of each class. And in the code I provided in GitHub, I made sure that when you pick randomly, you don't pick the class. We don't want to repeat each other. We want, if we pick 3 images in this step, we want to make sure that we are picking 3 unique images. We don't want to end up picking also the class. So now, if we picked 3, this will be the 4th image from each class. So the second step, so we have 5 classes, sorry. Those are here. I'm showing what the center image looked like. And the third thing, the last part, is the outliers. Remember in the first figure, I showed you some outliers. So each class would have an outlier, which is an image that is a bit far from the other images in the class. And in the code I provided with you, it was measured using Euclidean distance. So it will be finding the distance. So each class, now we're not making in the whole data set, but in class 1, for instance, in class 1, we had 166 images. We tried to find the furthest, the far of those images from the center of its respective class. So here I'm I'm showing an example of some outliers. So as you can see, that represents the images, but that's really a bit different. That represents the images in its class. So as you can see there's a difference. Like those outliers belong to this class, but they're different. But as you know, you wanted the algorithm to classify in 5 classes. It doesn't know anything except that it should give you 5 classes with with its content. So again, there are 3 stages. The first stage, you select the number of classes you want to put your unlabeled data. Nothing is labeled. The number of classes you want to put your unlabeled in. You pick an n number of images from each class, but make sure if you pick 3 from class 1, you pick 3 from class 2 and from each class. The second step, you pick the centroid of each class. And the third step, you determine the outliers. Now, here you pick only one. The outliers, you can pick anyone. It's the same as the random step here. You can pick any number. And I will show you in the example here how many images I picked. So let's see here. Let's see here that those are the 3 main stages in diversity sampling. After putting 5 classes, I picked 10 random images from each class. And sorry, in the next slide, I will show you the number of the amount of oh no, I show it here. Sorry, I select 10 random images from each class. I select the centroid image, and I picked 5 outliers. And in the code in GitHub, it's the same thing as we did with the uncertainty score, but here it's about the distance. So it will group the distance in ascending order, in descending order from the top to the bottom. So when we say that 5 outlier images, this means the top 5 images that are far away from the center. So 10, 1, 5. So each class we will be picking in our first iteration 16 images per class. And those are examples I picked them randomly. So those are some, when I picked the 10 images from the different classes and the centroid and the outliers, those are samples of images that the radiologist will be labeling. As you can see, there is some challenges in the images. Here they call the echogenicity here. Like in the ultrasound terminology, there's something called hyperechoic pixels. Hyperechoic pixels means light pixels, but most of our data set didn't have this artifact. But using this, we were encountered with that. So as you can see, we're picking some challenging cases and rare cases at the same time. Here I know there's 2 minutes left, but if anybody is okay, I might exceed 5 minutes of the time. I totally apologize. Maybe I will just 5 minutes. So I will go very quick, but as mentioned, we follow up if you have any questions after that. I will share everything with you. Let's see the effect now of diversity sampling. I provided one iteration to make it quick. So we started with 2 images. As you saw, we had a 56% accuracy. Now the reason for the 80 images, because if you multiply 16 times 5, because we're taking 16 images from each class plus 2, you will end with 80 images. Sorry, without 2. But yeah, it's just a calculation step. Yeah, it's like just 10. Sorry, so it's 10 plus 1 plus 5. So you're taking 16 images eventually from each class. And as you can see, 80 plus 2, so using 82 images, you got an 82%. So that's the main message I want to deliver today. Using uncertainty, we used a very simple classifier. We used uncertainty sampling. We were able, using 152 images, to reach around 87%. And as mentioned before, MLP mixer, ResNet, let's say ResNet because it's more common. ResNet 18 and even maybe 50. It's a very deep convolutional neural network, which most people have been using it a lot. Using 900 labeled images, the most it could achieve was 73%. So now here 150 images. Now here we're talking about 82 images. And those are the only images that your radiologist needs to label. But as you can see, using this method, it's expected that you, from now on, you should not worry, especially if you're working on a supervised learning algorithm, which is most of the time we're told that it is data hungry. Be prepared that you need to label thousands of images. From now on, using active learning and using those methods, and even if you combine them together, you would even get less data. You can reach a state-of-the-art performance with few labeled images. Yeah, so that's the main message, and I will, in 5 minutes, that's the last part in my presentation. It's about the importance of labeling instructions. We're talking about labeled data, but we don't need to forget that if we're sending that data to a domain expert or to someone to label our data, we're sure that our data will be labeled correctly, because we will have the same issue. Like we think that we applied active learning. We think that we should end up with less data to train our algorithm. But if we're not labeling the data right, that's very dangerous. And I really recommend this paper. It's also mentioned on GitHub as a reference, so you don't worry about like recording the name or link. But this paper was published in 2023, and I first encountered that paper last year. It was on arXiv, but then it was published in Nature recently on July. I really recommend that. And this paper wants to emphasize how important your labeling data is, how important your labeling data is, and if the domain experts, now talking to the domain experts like radiologists, if they want to label this data, how important that they have a record of how data is labeled, because sometimes that radiologist might ask like a new, like a resident or a new person in the field to label the data. There should be a way to transfer this knowledge, and even to transfer this knowledge to a technical person. There are some situations, because you don't, even if you want to label 400 images, maybe the domain expert doesn't have time at all. But if he can provide you with some labeling instructions that you can mimic, you as a non-medical person or a non-domain expert can label the data. So that's what the paper in brief wanted to deliver. So here the paper said that the high quality, we have to like emphasize this part, because now from all this today's tutorial, the value of our work is the data. So if the data is bad, by default everything will be bad, because I put the model alone, for instance, the classifier. I'm not focusing on the architecture. I'm focusing on the data. I want high quality data, because I picked the data. I did my job as a machine learning researcher, but the domain expert, I want to make sure that the data coming back is labeled correctly. So this paper emphasizes that there is a bottleneck. And I'm not talking about the number now. We agreed that a large amount of labeled data is something hard to obtain. Here I'm talking about the data that you picked, like the labeling itself. It's a bottleneck, and it's crucial for model performance. And they found that now you say I can outsource that to a crowdsourcing company. They're everywhere now. There's many labeling companies out there, but many of those labeling companies, they don't use domain experts. They might use sometimes medical students, like studying in their early days, and they want to have some extra cash. They might use them to label that. There's, for instance, Amazon Turk. Many people still till now using Amazon Turk to label data. Many people there are not paid a lot, so they want to achieve the labeling task very quickly. So they found, like in the paper, when you got the paper, they did a deep analysis of that. So it's not like a conclusion that came very quickly. They saw this company, the companies, and the effect. But they saw that also outsourcing your data, like you sampled your data, you did your job, but even sending that to a crowding they called crowding platforms because they use people from everywhere, regardless of the background, to annotate the data, and even to professional networks. Because you don't know how advanced the domain expert is, they found the bottom line was the annotation was poor. So you have this problem, you didn't solve anything. And so why do we need the labeling instructions? At the end, we need them because if you have non-experts in your team, even with no medical background, they might need that to expedite or put the effort in labeling if you need more data. And the inter-rater variability means the differences between the health professionals themselves and even from the professional himself or herself. Like they might label the same image again in a different way. So you want to reduce this inter-rater variability. So that's the goal of the labeling instructions. And yeah, those are the limitations now, that if you're even sending data to more than one domain expert, you will find some differences in their annotations. And I saw that. Like maybe two radiologists might label, you're asking the same question, I want you to label this organ, for instance, but you get back different results. So which one to pick? And if you have limited domain experts available, sometimes you need to send this task to non-medical experts. So that's the goal of labeling instructions. The last two slides, and I appreciate everybody's time here. The bottom line is that they found that they wanted to test. Now they agreed, after doing a comprehensive study, that labeling instructions are important, are crucial to performance. But how should they look like? So they found that if the labeling instructions performance, like if the people to label, like let's say here they are non-domain experts or non-professionals or mature or entry-level professionals, if they were presented with minimal text, the performance wasn't that much. Let's say that's the maximum performance they could reach. They said, like, what if we because I will show some examples in the next slide. That was like some few instructions. They said, what if we added more instructions to this document? They found if it is written, nothing changed. So it means that even if your instructions are detailed without any figures or examples, nothing will change. So text alone doesn't work. So they found that if we combine extended text, so this part, with figures, the performance will be higher. And those are some examples. So here, this is an example of some instructions, like what to do, like how to do, like they're sending that to some non-expert and telling them to annotate the medical instruments in the figures. So they told them here what the medical instrument is by definition. Here, the extended text looked like this, which, as we saw before, it didn't make a difference. But when they were presented with instructions like the text, a definition of the medical instrument, how it looks like, and how you will annotate it, that differed a lot. And yeah, I will stop here. I really can't thank you enough for all your time and patience waiting. I will just I know everybody needs to leave. I will just share where you if you want. I will share just the tutorials. The tutorials website. There you will find my contact, the GitHub page, and yeah, I know there's no time for questions. I really apologize. I even exceeded the time, but we can if you have any questions, please feel free to reach me by email, or even if you want to discuss on GitHub. So again, I can't thank anyone enough. Yeah, for that. And thank you for your time.
Thank you very much, Abder, and thank you everybody for being here.
Yeah, I thank
We
you
really
for all
appreciate
your
it.
patience and staying for all that time. It's highly appreciated. So yeah, hopefully we can connect together. So yeah, again, you have my information, GitHub, and yeah, if you have any questions about the code, we can discuss further. Yeah. So take care, everyone, and have a nice day.
Thank you.
Thank you so much.
Thank you. Have a nice day. Thank you very much.
Thank you.